In this video, we will look at some of the key considerations when implementing our own libraries of functions. In previous lectures, we have already seen how we can create our own user-defined functions. A user-defined library is a collection of such functions. Typically, the functions within a given library will be related to one another in some way. For example, maybe we are working on various urban modeling scripts that are all generating massing models. We may then decide to create a library of urban massing functions. The libraries may be only for our own use, across different scripts. Or we may plan to share them with other people. Either way, we will need to design the library to make it easy to use. For function libraries, the key issue is designing the function signatures. Function signatures define the function name, the parameters, and the return values. They describe those aspects that a user of the function will be exposed to. This is also sometimes described as an interface. They do not describe how functions are implemented internally. After defining the function name, then the next thing to decide is the function parameters. First, it is important to try and minimize the number of parameters. Functions with many parameters are more difficult to use, and the semantics may be confusing. The order of the parameters is also important. In theory, the actual ordering does not matter. As long as we put the arguments in the correct order, the result will be correct. But in practice, we should try to use an order that makes the function easy to understand and use. If the function requires many inputs, then multiple values can be wrapped up in a single complex data type. In this example, a list is used to pass in 3 values, 2 numbers and a list of 3 numbers. The problem with this approach is that it is difficult to know what these numbers are. The user will have to try and remember what each number in the list represents. This can be error-prone. An alternative to using lists is dictionaries. In a dictionary, each entry has a key and a value. The key is typically a string. This key can capture the semantic meaning of the data item. In the example, we can now get a better sense of how the 3 values from the previous example might be used. The semantics is clearer. Dictionaries also allow us to specify only some entries. For any missing entries, the function can supply its own values. In the example, the dictionary did not include an entry for center. Assuming that this is the center point where some geometry may be generated, the function may default to using the origin of the global coordinate system as the center point. Another aspect to consider is overloading our functions. This may reduce the number of separate functions that are required, and it may also make it easier for the end user. A typical example is overloading a function to accept either a single value or a list of values. If a single value is provided, the function processes the value and returns the result. If a list of values is provided, the function loops over all the values, processing each one, and then returns a list of results. Next, we will look at return values. Functions always return either nothing, or they return one value. If multiple values need to be returned, then we can again use a complex data type. In some cases, lists of values can be used. However, there may again be an issue with semantic legibility. In the example, the function returns a list containing 2 lists, polylines and polygons. But it may be easy to forget the order. The dictionary may again be preferable, due to its ability to more clearly capture semantics. In the example, we can see there is no risk of confusing the polylines with the polygons. For both lists and dictionaries, destructuring can be used. It is semantically clearer, and it requires fewer lines of code. When destructuring, the left-hand side of the assignment can contain multiple variable names. If we are destructuring a list, then we specify the variable names in square brackets. If we are destructuring a dictionary, then we specify the variable names in curly braces. In both cases, the variables will be assigned values from within the returned data structure. Another option is to use parameters instead of return values. Remember that any complex data type is passed by reference. This means that if we pass in a list or dictionary into a function, the function can update the values inside that data structure. There is then no need to return the data, since the changes that the function makes will also be visible outside the function. With this approach, the last parameter in the function is typically used to capture the result. In the example, an empty dictionary is passed in as the last parameter. The function will then populate this dictionary with the results. In other cases, a dictionary with existing data may be passed in, and the function may modify some of this data. Here is another example, using a list. In this case, the function filters out null values out of the list. The function updates the list that is passed in, so no value needs to be returned. Next, we will briefly mention documentation and testing. If our library of functions will be used by others, then documentation will be important. Even for libraries only being used by us, documentation may still be a useful reminder. The documentation should focus on how to use each function. For example, a high-level overview of what the function does, together with a description of the parameters and return values. The documentation does not need to describe how the function was implemented internally. Finally, we will briefly look at testing. The aim of testing is to verify that our code actually works. Usually, this is an iterative process of finding and fixing bugs. Broadly, testing can be broken down into 3 levels: unit testing, integration testing, and system testing. The pyramid diagram suggests that the most effort should be expended on unit testing, and the least on system testing. However, note that there are many schools of thought on this. Unit testing focuses on testing small pieces of code in isolation from one another. Usually this will be an individual function. For each test, some test data will need to be created. The automated test will compare the output of the function to a known correct answer. If the values match, then the test passes. If not, then it fails, and the function implementation will need to be fixed. Integration testing goes one level up, and tests how different functions work together. Even if all the functions are passing the unit test, new bugs may be discovered when those functions are combined. Finally, system testing focuses on the whole system. It is also sometimes referred to as end-to-end testing, or E2E testing. This will test how the end user will use the system, including various possible interactions through the UI.